Now let's talk about how crash recovery and logging are done in xv6. So what happens in xv6? On our right, we're going to add the block number to an in-memory array. So what happens is this is going to basically be a log array in memory. Let's say we've got a create, and it's updating 2 blocks. It's updating the inode block, and it's also updating the directory entry block. So we've got 1 and 2. So this is the inode block, and this is the directory entry block. And so what's going to happen? So these are in the buffer cache. Okay? And they're pinned. So other buffers in the buffer cache might be able to be evicted, but these cannot because we're still in the middle of our create. So what's going to happen now? We do the commit. Right, this is part of this system call of the create. It updates this iBlock, updates this iBlock, and says, okay, commit. So what's going to happen? The first thing we want to do, we forgot that we have these block numbers. So let's say, when I say 1 and 2, let's actually put the real block numbers there. Okay, so instead of 1 and 2, this is 135 and 273. Right, so they're part of this buffer cache. We've now got our disk, and a portion of this disk has the log. So we've got the file system here, we've got the log here, and the entire thing here is our disk. So what we're going to do is we're going to write these buffers to the log. We also forgot to mention, we write down the 135. So, and the 273. So as we are updating this inode block in memory, and signaling that we want to write it to the log, that basically pins it and takes the number and writes it in here. And then we do some more manipulation, we update the directory entry, we say we want to write it to the log, that pins it and puts it in here. So we're going to write these to the log. We can actually issue a request that just says I want to write these 2 buffers to the log, but I don't want to write them to 135 and 273. I want to write them to my log locations. So I'm going to write them actually here. So this is the contents that we want to go to 135. This is the contents we want to go to 273. And we're going to actually keep a header. Right, so this header contains the block numbers, right? Because the block numbers aren't inside the blocks just have the text. So we are going to have 2, which is the number of blocks, and the block numbers, 135 and 273. So this contains all the information that we need here. The commit is actually going to be writing this header with a non-zero block number, or it's non-zero number of blocks. So it's the header that keeps track of whether it's done or not. If this is non-zero, it's done. Now, after the commit, we do the install. How does the install work? The install goes ahead and writes these blocks. First thing to note, actually, when we were committing and writing this, we could write these quickly because we're writing them to sequential locations on the disk. So we don't have to do any seeking as we're doing these writes. We can just say, write this big chunk of data or all these blocks into these sequential locations. So that's good. So we're, writing to location K plus what, and the header is presumably K minus 1. So after the commit, then we go ahead and write 135 to its proper location. So this is the install. We write 273 to its proper location. And then we need to mark it as not done. So what will we do? We'll mark this as 0. Just erase those. And we'll now write this back to the log. So now if we look in the log says no, it's not done. The other thing, by the way, I'm sorry that I forgot to point out, is during the commit, so as we're committing, we write 135, we write 273, we write the done. Now we can go ahead and clear this out and unpin these. So if they were pinned before, now they're unpinned. So if we have a 0 in this log header block saying the number of blocks, and that means that we have not committed. We might have been in the middle of writing things here. We're just not committed. Okay, and so therefore there's no reason to replay this. If there is a non-zero, then that means we have a commit, but we didn't finish the install. So it was between the commit and the install. So we can kind of look at it like this, that let's look at it this way. So here's our commit point. So our commit point tells us whether we should go forward or go back. Once we're committed, right? So if we commit, then from that point on, we're going to go through and do the install. However, if we don't make it to the commit point, then it's as if we never did the system call in the first place, as far as the file system was concerned. And so this is sort of start the system call, and this is end the system call with it completed. Okay. So after the commit point, we're guaranteed to have the results of this system call preserved on the file system no matter what. Before the commit point, we won't at all. So nothing of those blocks will make it. One thing that's important is that means that a system call, the writes have to fit into log. We've got some fixed size log here, and it's got to be big enough to handle any system call. So we're going to set this size big enough to handle any system call. That means that some system calls we may have to break apart, where really it's unbounded. So let me give an example of that. Let's say we do a large write. So need to break up. So we need to break up into multiple transactions. We may have to break up a large write. So if a user program, let's say, issues a write, I don't know, 500 megabyte write, it's unlikely our log is going to be big enough for that. So instead, we'll break it apart. That means that the write is not itself atomic, because of the fact that we are breaking into these multiple transactions. But what we are guaranteed of is the fact that if we do a large write, like let's say we are writing this entire sequence, that we will end up with some prefix of it. So either, let's say we break up this large write into 10 separate transactions so that each transaction can fit into the log, then what we're guaranteed with is either we'll end up with no transactions having running, so none of it happened, or we'll do the first one, or we'll get the first two, or we'll get the first three, or the first four, all the way to the end. So we'll always get some prefix of the requested write. We also have to consider the fact that we're running multiple threads on multiple processors, and we may have multiple system calls running concurrently. So we might want to have, for performance reasons, writes from several system calls in the log. Okay? So we have this situation where we've got multiple system calls happening. So we've got, let's say, this system call, and this system call, and this system call, right, all occurring. We want them all to be in the log. So on a commit, we have to write them all. But we can't do that if we're still in a transaction. So let's say this system call took longer than these two system calls, and we were writing blocks to the log, right, where what I mean by writing them in the log actually is putting them in the buffer cache and storing them in the in-memory array. So we wrote one here, and we wrote one here, and we wrote one here, and now we're done. And we wrote one here, and we wrote one here. And here we wrote one here, and here. When we get to this point, these two system calls are done as far as they're concerned. They're done all their writing. But this system call is still in progress. So therefore, we need to go ahead and not write the data from these. So how are we going to do that? What we're going to do is we will go ahead and wait for all the in-progress system calls to finish, and then we'll commit them all at once. When we start a system call, what we're going to do is look and say, will this data fit in the log along with the other in-progress system calls? If not, we're going to just wait. That is, we'll sleep. And we'll wait for the current calls that are in progress to complete and commit, and then we can go on. So we have these transactions. We're going to look at what happens with multiple simultaneous system calls, right? Because they might be running multiple system calls on different CPUs, for example. So the one system call begins its transaction. So it begins, and let's say we actually have a call to begin the transaction. So this is system call 1, and we begin our transaction, and time is going over here. So it begins its transaction, and then goes and writes to one block, and then continues on, writes to another block, and then finishes. So this is the begin, and this is the end transaction. At this point, it's the only system call running that's made any changes to the log, and so these log entries just go and get written to the log on disk, and then they get installed, right, do their thing. However, let's say that instead, along calls another system call before this finishes. So this one starts, let's say, here. And runs and ends here. So now 3 of these are in the log. Well, when this first system call ends its transaction, can we actually write our log to disk? No, because that would write these 3 blocks, and we have no idea at the time that this occurs whether there's any additional block. In fact, there may be a block written here. So we would just write 3 of the blocks instead of all 4 of the blocks. So we want to commit only if the number of transactions in progress equals 0. So in the first case, when this is over here, during this, transactions progress was 1, and we got to the end, we decrement to 0, and then we'd commit. Now we get to the end here, and we would not commit. Because the number of transactions in progress was 2 at this time, now it's 1, we need to wait for it to get to 0. This end will actually do the commit. So only the end, only the last end will basically do that. What happens if we just have simultaneous system calls running and running and running? Doesn't this mean that we're going to wait forever for committing? Not quite. Let's imagine that we have a relatively small log that can only hold this many blocks. And now system call 3 comes along. So it comes along, let's say here, tries to do a begin. It's going to look and see that the number of blocks in the log is not going to be enough. And so therefore, it's going to block on the begin. And by block, I mean sleep. And it's going to just have to wait until the commit has happened for the current in progress calls. So it will sleep to heap. This guy is going to do the commit, which will write them out to disk, do the commit, do the install, and then wake up sleepers. Wake up whoever was blocked. And they'll then go ahead and start another big log transaction. Let's talk about what happens if we have a block that's written multiple times in a transaction. Let's look at how that could happen. So we could have two system calls both writing to the same file, for example, or two different system calls that are changing different inodes, but those inodes are in the same block. So as we look at a particular block, this block may be written by syscall 1 and also written by syscall 2. So what happens? Well, that's actually just fine. If we think about it, right, in the buffer cache, this is in the buffer cache. And pinned, in fact. And these will both be in the same transaction. They have to be in the same transaction, right, the same big log transaction, because they're both currently running. And if they run in the same transaction, then one of them would have been blocked before it started writing. So what happens then is that this block is going to get multiple writes from multiple system calls, and yet only get written to the disk once. So this is actually called write absorption. We are absorbing the multiple writes into a block and turning that into a single write onto disk. Or in our case, really two, because we write once to the log and then we write from the log to the final location. So that'll be okay. That just means, again, when this block gets written to disk and committed and installed, it's going to get the results of both system call 1 and system call 2. So we'll see either both system call 1 and system call 2, or we'll see neither of them. They'll all be part of this large transaction. We talked about the disk layout on xv6. So 0 is unused, 1 is the super block, 2 through 31 are the log, and then 32 starts the inodes, and we got other stuff beyond that. So this is the key here, right? 2 through 31 is the log. We have 30 blocks total. So that means we can really support, we're going to need some log header. Let's say that's one block. Then that's 29 blocks we can actually support. So that's any given transaction can support no more than 29 blocks. Let's look at an example. So let's say we go ahead and echo. So we're going to echo A into X, and let's look at what blocks actually get written on disk. So first we have the system call create. The first block that's going to get written is block number 3. Okay, so that's part of the log, and this is the inode. The second block is block 4, and that's going to be the directory entry. Okay. And then we're going to write block number 2, which is the log header. This is the commit point. It's a commit point because we have written now that the number of blocks is 2, so it's non-zero. Then we'll go ahead and actually write block number, let's say 36, which is the inode. So that's basically copying, right, this one here. So if we looked at the log header, right, the log header would have a 2 to say that that's the number of blocks. It would have a 36 to say that's where this block 3 actually, its final destination is. And then we could look at, let's say, 54, which would be the directory entry block, the directory data block. And so we'd have a 54 in here too. At this point, are we done? No, we're not done because we haven't marked that the commit is complete. So now there'd be another write of 2 with the log header. And this would show that there are 0 entries. That is one system call. Let's look at one more system call where we're actually writing into X. So we're going to do the write system call. And again, these are the order things are actually written to disk. Well, let's just correct one thing here. This is probably not 54 because we need to be out where the data blocks are. So let's call that 99. All right. So the first thing we're going to do is we're going to go ahead and write the free bitmap block, because the first thing this will do is allocate a data block. So we'll go ahead and write, right, we know we're going to be writing 3 and then 4, and so 3 is going to, let's say, write the free bitmap. That's 56. And then 4, we're going to go ahead and write the file content. That is the A, and that'll be, let's say, 136. And then what have we got to write? Well, we've got to update the inode, right? Because we've got a size in the inode that is now 1 instead of 0. So the inode was 36. And, right, this is just commentary on this. We're actually just writing these blocks 3, 4, and 5. This says what's in it. Now we're going to write 2, and this is the log header. This, again, is the commit point. Our log header is going to look like 3, 56, 136, 36. At this point, we need to do the install. So we're going to write 56. We're going to write 136. We're going to write 36. And then we're going to go back and write 2, which is the file header, which will just have 0. So that, I hope, shows you how the xv6 logging is working. We'll look at the code next.